Section 1 Introduction. We're here to discuss the role of large language models, LLMs, in tasks such as understanding common sense and generating code. Despite their success, these models often struggle with mathematical reasoning, producing inaccurate or nonsensical content. Previous attempts to address these issues include the chain of thought (COT) framework, which improves LLMs' logical reasoning by generating intermediate steps in their reasoning process. Another approach, PAL, uses the Python programming interpreter to enhance computational accuracy. Recently, OpenAI introduced an improved version of GPT-4, known as GPT-4 Code Interpreter or GPT-4 Code. This model excels at providing logical reasoning in natural language and generating Python code step by step. It can generate and execute code incrementally, and then present the output of the executed code back to the LLM. This combination of code generation and execution with natural language outputs has shown promise in solving mathematical reasoning problems. Our initial tests show that GPT-4 code achieved an impressive zero-shot accuracy of nearly 70% on the challenging math dataset, a significant improvement over GPT-4's performance. Despite GPT-4 code's proficiency in solving math problems, there hasn't been a systematic analysis focusing on understanding and enhancing its mathematical problem-solving abilities. A key difference between GPT-4 code and its predecessor, GPT-4, is GPT-4 code's ability to automatically generate and execute code. In this paper, we present preliminary experiments that investigate GPT-4 code's code generation and execution mechanism using specific code-constrained prompts. Our analysis reveals that GPT-4 code's strong performance is not only due to its code generation and execution abilities, but also its capacity to adjust its problem-solving strategies based on feedback from code execution, a process we call self-debugging. Because code generation evolves its reasoning step by step and performs self-debugging after code execution errors, there is an increased frequency of code usage. Therefore, we introduce the concept of code usage frequency to quantitatively analyze the impact of code-constrained prompts on GPT-4 code's mathematical problem-solving. However, the self-debugging mechanism only verifies each step of the generated code and lacks the verification of the reasoning steps and the final answer, which is crucial to the math problem-solving abilities of LLMs. We therefore ask, can we fully exploit the code generation and self-debugging mechanisms in GPT-4 code, so that it can automatically verify and correct its solutions, without extra help from other models or users? To answer this, we propose a simple yet effective prompting technique called the Explicit Code-Based Self-Verification, CSV. This technique guides GPT-4 code to generate additional code that verifies the answer and adjusts the reasoning steps if there's a flaw in reasoning. Unlike previous methods that rely on external language models for verification, our approach leverages GPT-4 code's inherent strengths. This approach offers two key benefits. 1. When the verification indicates an answer is false, GPT-4 code can rectify its prior solution and provide an improved alternative. 2. Solutions verified as true tend to be more reliable, similar to human problem solving. However, even if a solution is self-verified as false, we do not directly abandon it. Instead, we propose a weighted majority voting strategy that incorporates the code-based solution verification results, as opposed to relying exclusively on the frequency of answers. We assign different weights to the solutions according to their verification states, reflecting the solution's varying levels of reliability. Our explicit code-based self-verification prompt boosts GPT-4 code's accuracy in mathematical problem-solving with increased code usage. Empirical study demonstrates the effectiveness of our proposed framework on the math, GSM-8K, and MMLU math datasets using GPT-4 code. Our approach achieves an impressive accuracy of 84.32% on the math dataset, greatly outperforming the base GPT-4 code and previous state-of-the-art methods. In addition, we are making our experimental data on the MMLU math and math datasets publicly available, enabling result replication and facilitating fine-tuning of open-source LLM models to further enhance mathematical problem-solving capabilities with the assistance of code generation. In summary, this paper's main contributions are threefold. 1. We provide the first systematic analysis of code generation, execution, and self-debugging's role in mathematical problem-solving. Our findings reveal that GPT-4 code's impressive mathematical problem-solving proficiency is primarily attributed to its step-by-step code generation and dynamic solution refinement based on code execution outcomes. 2. We introduce the innovative Explicit Code-Based Self-Verification, CSV, prompt, which leverages GPT-4 code's advanced code generation mechanism. This prompt guides the model to verify the answer and then reevaluate its solution with code. CSV not only extends the verification to the logic behind problem solving but also improves the efficacy of the majority voting method by integrating the verification states. 3. We have contributed to the LLM community by creating 2 new instruction following datasets, MathCode and MMLU MathCode. These datasets are designed to enhance the mathematical reasoning capabilities of open source models. Section Summary. The paper introduces GPT-4 code, an improved version of GPT-4 that combines natural language reasoning with step-by-step Python code generation and execution. The authors propose a prompting technique called Explicit Code-Based Self-Verification, CSV, to enhance GPT-4 code's mathematical problem-solving abilities. The CSV prompt guides the model to generate additional code for answer verification and solution refinement, resulting in significantly improved accuracy on the math dataset. Section 2. Related work. In this section, we'll discuss related work in the field, focusing on 3 main areas: chain of thought reasoning, solving math problems with code, and self-verification. Starting with chain of thought reasoning, a significant contribution in this area is the chain of thought, COT, prompting approach. This method demonstrates the ability of large language models, LLMs, to reason in multiple steps. By simply adding the phrase, "let's think step by step," before questions, a strong zero-shot baseline can be established. Further studies have expanded on this by improving self-consistency through majority voting, selecting few-shot examples, and creating output chains with more complex reasoning steps. They've also simplified problems into smaller subproblems and even expanded the chain of thought concept into a tree of thoughts. Our method is similar to this, as we also use step-by-step, like prompts to guide the use of code by GPT-4 code. However, we've improved on the majority voting concept by introducing verification-guided weighted majority voting, which uses the results of CSV as voting weights. Next, we'll discuss solving math problems with code. It's been observed that large language models are not always accurate when performing arithmetic calculations. As a result, previous research has attempted to solve math problems with the help of code. For example, the GSM-8K dataset uses calculation annotations to extract all arithmetic calculations solved by an external calculator, specifically the Python eval function. Other methods, such as the Program-Aided Language Model, PAL, and Program of Thoughts, POT, interpret math problems as Python codes and execute these codes with an external Python interpreter to get the answer. While these methods can provide more accurate answers than some non-code methods, they often produce codes with execution errors or incorrect answers due to a lack of a verification mechanism. Our approach improves on this by using GPT-4 code to generate multi-step codes and refine codes that fail to run. We also use CSV to enhance the reliability and accuracy of the answers. Finally, let's talk about self-verification. Human problem solving often involves iterative thinking, verification, and refinement. Unlike previous studies that train an additional verifier to check the correctness of final answers or intermediate steps, some research has shown the self-verification abilities of LLMs by generating multiple answers and ranking them by self-verification scores. The self-refine method takes this a step further by iteratively refining its output through self-generated feedback. Our method differs from these self-verification methods as it uses generated codes to verify the answers and votes on different answers based on the verification results. This improves the accuracy of the verification and makes full use of the information in the verification process. Section Summary. The chain of thought, COT, prompting approach showcases the multi-step reasoning capabilities of language models. Our method builds on this by applying step-by-step prompts to improve the reasoning abilities of GPT-4 code. Additionally, we leverage code verification and self-refinement techniques to enhance the accuracy and reliability of the answers generated by the model when solving math problems. Section 3 Method. We initially carried out a preliminary experiment using GPT-4 code on the challenging math dataset. Impressively, it achieved an accuracy of 69.7%, which is a significant improvement over the previous best performance of 53.9%. This promising result from GPT-4 code encouraged us to delve deeper into its underlying code mechanisms. In one section, we demonstrate that the robust performance of GPT-4 code in solving math problems comes not only from its ability to generate accurate step-by-step code but also from its self-debugging mechanism. In another section, we aim to harness the self-debugging strengths of GPT-4 code to further enhance its ability to solve mathematical problems. In our pilot experiments, we sought to understand the impact of code usage on GPT-4 code's math problem-solving capabilities. We did this by limiting GPT-4 code's interaction with code through carefully designed prompts. We introduced two code-constrained prompts and a basic prompt for comparison. Prompt 1. No code usage is allowed. In response to this prompt, GPT-4 code is not allowed to incorporate code into its solutions. This forces GPT-4 code to rely solely on natural language (NL) reasoning chain, similar to solutions in the COT framework. The resulting sequence of reasoning steps is depicted as C_script style NL, with an example given in Fig. A. Prompt 2. Code can be used only once. In this setting, GPT-4 code is allowed to use code only once within a single code block to generate the solution, similar to the PAL approach. We denote this sequence as C_script style SL, representing a series of symbolic language SL, such as Python. An example is shown in Fig. B. Basic prompt. GPT-4 code is prompted to tackle the problem without any restrictions on code usage. This leads to GPT-4 code's typical functioning pattern, which can be denoted as C=C1_script style NL, C1_script style SL, C2_%script style NL, C2_script style SL, dots, representing a sequential list of reasoning steps, each consisting of both natural language and Python code, with an example shown in Fig. C. We also introduced code usage frequency to record the number of times the code was executed for different prompts. The results of the experiments using these prompts are shown in Fig. B. This figure shows a positive correlation between the better performance of GPT-4 code and the higher code usage frequency. Specifically, Prompt 1 results in almost no code usage, while Prompt 2 results in approximately 1 times code usage. Prompt 2 yields an accuracy gain of 6.9% over Prompt 1. This suggests that the Python code chains, C_SL, can improve computational capability more than the natural language chains, C_NL. This observation is consistent with the findings in previous Python-based prompting methods. However, using code only once has a drawback. The model lacks the ability to self-debug when the code output triggers an error or produces an implausible outcome. The basic prompt consistently produces solutions that involve multiple instances of code usage, resulting in a high code usage frequency. Additionally, the basic prompt shows a notable increase in accuracy. These improvements in code usage frequency and accuracy might be due to two unique advantages. 1. Generating code in brief and frequent segments, divided among natural language reasoning steps, tends to result in higher accuracy. 2. The model has the ability to evaluate the results of code execution and make corrections to solution steps if the outcomes contain bugs or are deemed illogical, as illustrated in Tab and Tab. From these observations, it seems possible to enhance and build upon the favorable attributes of GPT-4 code, to further improve its precision in tackling math problems. Section Summary. In this section, the authors conduct a pilot experiment with GPT-4 code on the math dataset and achieve an accuracy of 69.7%, surpassing the previous state-of-the-art performance. They then explore the code mechanisms of GPT-4 code and find that its ability to generate accurate step-by-step code and self-debugging mechanism contribute to its robust performance in solving math problems. By constraining GPT-4 code's code usage through different prompts, they observe that allowing code usage multiple times leads to higher accuracy and the ability to self-debug, while using code only once improves computational capability but lacks self-debugging ability. These findings suggest potential ways to enhance GPT-4 code's mathematical problem-solving ability. Section 3.2 Explicit Code-Based Self-Verification Prompting. We're inspired by the findings from our analysis of code usage frequency, and we want to leverage the abilities of GPT-4 code. This model is great at generating accurate code, evaluating the results of code execution, and adjusting the reasoning steps of solutions when necessary. However, it currently falls short in ensuring the correctness of solutions. So, our goal is to use these strengths to enhance solution verification. To do this, we suggest a method called Explicit Code-Based Self-Verification, CSV. This method prompts GPT-4 code to validate its answer by generating code. By doing this, we add an extra verification stage to the solution, which we'll call V. The outcome of this verification can be classified as true, false, or uncertain. If the outcome is uncertain, it means that GPT-4 code had trouble finding an effective way to verify the answer, so it doesn't provide a definitive verification result. Using GPT-4 code's autonomous abilities, we can describe the proposed prompting as follows. The solution leads to the verification outcome. If the outcome is true, we get the final answer. If it's false, we generate a new solution and verify it again until we get a true outcome and a final answer. If it's uncertain, we also get the final answer. With CSV, the model can use code to verify answers and then review and adjust its solution if the verification result is false, with the goal of getting the correct answer. We expect this to significantly improve accuracy. Both the verification and correction stages are based on code, which will increase code usage frequency. We've conducted experiments with CSV, and the results show that our CSV prompt consistently outperforms the basic prompt in terms of accuracy across all difficulty levels. Also, code usage frequency clearly increases. Before GPT-4 code, previous frameworks relied on an external language model to use natural language for verification and well-designed prompts with a few examples. In contrast, our approach simplifies the process by using a straightforward prompt for GPT-4 code, without needing any examples. This allows GPT-4 code to independently verify and correct its solutions using the advanced code execution mechanism, eliminating the need for customized examples. Since CSV can effectively verify problem-solving answers, we can integrate the verification states into a majority voting process, similar to the method used in self-consistency COT. Answers that are verified as true are generally more reliable, which reflects the problem-solving approach seen in human cognition. This improved reliability can be used in the majority voting process. To take advantage of this, we introduce verification-guided weighted majority voting, which assigns different weights to the states of the verification process. Sometimes, once an answer is confirmed as false, no additional verification is conducted, resulting in a false verification state. We assign weights to these states of true, uncertain, false. Like the self-consistency with COT-SC, our framework can sample multiple paths. For simplicity, we take pairs of final answers and their corresponding verification results from multiple solutions. The voting score for each candidate answer can be calculated as the sum of the weights for each verification state, multiplied by the number of times that state occurs for that answer. Finally, we select the answer with the highest score from all candidate answers. If all weights are equal, this becomes equivalent to the naive majority voting used in self-consistency with COT-SC. Typically, we assign a higher weight to an answer verified as true than to one with an uncertain verification state, and the lowest weight to an answer verified as false. Section Summary. The authors propose a technique called Explicit Code-Based Self-Verification, CSV, to enhance solution verification using GPT-4 code. By prompting the model to generate code for answer validation, the proposed method introduces an extra verification stage to the solution. The verification outcome can be true, false, or uncertain, and by leveraging GPT-4 code's capabilities, the model can adjust its reasoning steps to obtain the correct answer. Section 4 Experiments. We conducted several experiments to test our model's performance. One of the main tests was on the math dataset, which is known to be the most difficult math word problem dataset. We used this dataset for most of our experiments and analyses. Our model, GPT-4 code, performed exceptionally well on the math dataset, achieving a success rate of nearly 70%. This is a significant improvement over the previous best result of just under 54%. This demonstrates that GPT-4 code is highly effective at solving math problems, and we used it as our baseline for further studies. We then enhanced GPT-4 code by adding explicit code-based self-verification, which increased its accuracy to over 73%. When we added both explicit code-based self-verification and verification-guided weighted majority voting, with 16 sampled paths, the accuracy rose to over 84%. This impressive result is due to the strong capabilities of GPT-4 code, which our method was able to enhance further. However, we found that the extent of improvement varied depending on the subject. For example, the accuracy of solving geometry problems only increased by 0.6%, despite the original GPT-4 code accuracy being only 54%. This discrepancy could be due to the fact that solving geometry problems often requires multimodality, a concept beyond the scope of this paper. In addition to the math dataset, we also tested our method on other reasoning datasets such as GSM-8K, MMLU Math, and MMLU STEM. Our method outperformed other methods in these tests, achieving the best results across all datasets. We also compared our results with those of previous state-of-the-art techniques and open-source models. Our analysis showed that verification-guided majority voting is an effective way to reduce the number of sampled paths, compared to GPT-4 with model selection and PHP. We compared our model's performance with existing models on the MMLU math dataset and with the best open source models on MMLU STEM. The open source models were significantly outperformed by their closed source counterparts. To help close this gap, we plan to make our dataset publicly available in the near future. This will allow open source language learning models to fine-tune their capabilities. For example, the open source model Llama 2 could potentially use this data to improve its math reasoning capabilities. Section Summary. The experiments conducted on the math dataset demonstrate that our model, GPT-4 code, achieves a significantly higher accuracy of 69.69% compared to the previous state-of-the-art result of 53.90%. By incorporating explicit code-based self-verification and verification-guided weighted majority voting, the accuracy of our model further improves to 84.32%. Additionally, our method outperforms other models on various reasoning datasets, including GSM-8K, MMLU Math, and MMLU STEM, establishing itself as the state-of-the-art solution. Section 4.3 Code Usage Frequency of Proposed Prompts. In this section, we'll discuss the frequency of code usage in our proposed prompts and its impact on accuracy. Similar to the method we used in a previous section, we collected data to understand the relationship between accuracy and the frequency of code usage. We looked at this across different factors: the prompts we proposed, the subjects, and the difficulty levels. As shown in our figure, the model behaves as we expected when we add code-based prompts. Each line in the figure shows a clear upward trend, indicating that as the frequency of code usage increases, accuracy generally improves. This improvement is more noticeable at higher difficulty levels, while at lower levels, the increase in performance isn't as significant. We also found that the frequency of code usage increases as the difficulty level rises. This suggests that more complex math problems require more frequent use of code. It also implies that using code multiple times could be a key reason why our model, GPT-4 code, has an advantage in solving difficult math problems. Next, we compared natural language and code-based self-verification. To highlight the importance of code in the self-verification stage, we used a different prompt that asked GPT-4 code to verify the solution using natural language instead of code. The accuracy achieved with this method was slightly lower than that of the basic prompt. We also noticed a decrease in accuracy for 4 out of the 7 subtopics, suggesting that relying only on natural language verification can reduce accuracy and performance. On the other hand, code-based verification improved accuracy across all 7 subtopics compared to the basic prompt. We also analyzed a method called verification-guided weighted majority voting. We first created a confusion matrix, which recorded solutions with self-verification that matched the true and false states from 5 different sampled paths. From this data, we calculated precision, recall, and accuracy. The results showed that compared to accuracy, there were improvements of 22.3% and 5.6% in average precision and recall, respectively. This suggests that accuracy could be much higher if more solutions reach the verified true state before giving the final answer. Lastly, we conducted ablation studies on a hyperparameter in the verification-guided weighted majority voting method. When the hyperparameter setting was such that the weight of true was greater than or equal to the weight of false, the performance of the verification-guided weighted majority voting consistently outperformed the naive majority voting methods across all sampled paths. However, when we set the hyperparameter to certain values, the performance under this configuration was worse than the naive majority voting. Therefore, our proposed method, verification-guided weighted majority voting, is easy to adjust and robust.